Hello, my name is Nickolay Zosimovych. Welcome to this course, Avionics Engineering, the course in which you will understand the basic principles underlying the key or core avionics systems in modern civil and military aircraft, and their implementation using modern technology. Okay, so 1 second, please. I'm just sharing my presentation. Avionics, as I just mentioned, is a cornerstone of modern aircraft. More and more vital functions on both military and civil aircraft involve electronic devices, and after the after the cost of the airframe and the engine, avionics is the most expensive item on the aircraft, but well, worth very cent of the price. Many technologies emerged in the last decade that will be utilized in contemporary times. After proof of soundness in designs through ground applications, advanced microprocessors are finding their way onto aircraft to provide new capabilities that were unheard of a decade ago. The Global Positioning Systems, or GPS, has enabled satellite-based precise navigation and landing. And communication satellites are now capable of supporting aviation services. And thus, the aviation world is changing to satellite-based communication, navigation, and surveillance for air traffic management. Both the aircraft operator and the air traffic services provider are realizing significant benefits. Proposed course also aims to meet the needs of engineers at all levels working in particular areas of avionics who require an appreciation and understanding of other areas and disciplines. A further objective is to show the very wide range of disciplines which are involved in avionics systems. And these make the subject an interesting and challenging field. Familiar technologies in this course include databases, one type of which has been in use over the 30 years, head-mounted displays, and fly-by-wire flight control. New bus and display concepts are emerging that might displace these veteran devices. An example is the retinal scanning display. Other emerging technologies, including speech interaction with the aircraft and synthetic speech. Speech interaction may soon enter commercial service on business aircraft as another way to perform some non-critical functions. Synthetic vision offers enormous potential for both military and civil aircraft for operations under reduced visibility conditions, or in cases where it is difficult to install sufficient windows in an aircraft. This course offers a comprehensive view of avionics, from the technology and elements of system to examples of modern system flying on the latest military and civil aircraft. Apart from the interest inherent in aircraft, the range of disciplines and technologies which are exploited covers aerodynamics and aircraft control, satellite navigation, optical gyroscopes, man-machine interaction, speech recognition, advanced display systems, holographic optics, intelligent knowledge-based systems, closed-loop control systems, high-integrity failure survival systems, high-integrity software, integrated circuit design, and data bus systems. Personally, I have found avionics to be a very interesting and challenging area to work in, and I hope this course will help you all to share these skills. Avionics is a word derived from the combination of aviation and electronics. It was first used in the USA in the early 1950s and has since gained wide-scale usage and acceptance. The term avionics system or avionics subsystem is used in this course to mean any system in the aircraft which is dependent on electronics for its operation. Also, the system may contain electromechanical elements, right? Okay. For example, fly-by-wire or FDW flight control system depends on electronic digital computers for its effective operation. But there are also other equally essential elements in the system. These include solid-state rate gyroscopes and accelerometers to measure the angular and linear motion of the aircraft, and air data sensors to measure the high airspeed and incidence. There are also the pilot's control stick and rudder sensor assemblies and electrohydraulic servo actuators to control the angular position of the control surfaces. Modern general aviation aircraft also have a significant avionics content. For example, color head-down display, GPS satellite navigation systems, radio communication equipment. Avionics can account for 10% of their total cost. The avionics systems are essential to enable the flight crew to carry out the aircraft mission safely and efficiently. Whether the mission is carrying passengers to their destination in the case of a civil airliner, or in the military case, intercepting a hostile aircraft, attacking a group target, reconnaissance, or maritime patrol. A major driver in the development and introduction of avionics systems has been need to meet the mission requirements with the minimum flight crew. In the case of modern civil airliners, this means a crew of two only, namely the first pilot or captain and second pilot. This is only made possible by reducing the crew workload, by automating the tasks, which used to be carried out by the navigator and flight engineer. The achievement of safe two-crew operation has very considerable economic benefits for the airline in highly competitive market with the consequent saving of crew salaries, expenses, and training costs. Okay? The reduction in weight is also significant and can be translated into more passengers for a longer range on less fuel. In the military case, a single-seat fighter or strike or attack aircraft is lighter and costs less than the equivalent two-seat version. I hope you agree with me. Okay? Other very important drivers for avionics systems are increased safety, air traffic control requirements, all-weather operations, and reduction in fuel consumption, improved aircraft performance and control, and handling, and reduction in maintenance costs. Military avionics systems are also being driven by continuing increase in the threats posed by the defensive and offensive capabilities of potential aggressors. The role played by the avionics systems in modern aircraft enable the crew to carry out the aircraft missions can be explained in terms of hierarchical structures comprising layers of specific tasks and avionics system functions as shown in this slide. This shows the prime of core functions, which are mainly common to both military and civil aircraft. It must be pointed out, however, that some avionics systems have been left off this diagram for clarity. For example, the air traffic control transponder system, the ground proximity warning system, and the threat alert or collision avoidance system. That's called as abbreviation TCAS. All of which are mandatory equipment for civil airlines. It can be seen from this picture that the main avionics subsystems have been grouped into 5 layers according to their role and function. These are briefly summarized below in order to provide an overall picture of the roles and functions of the avionics systems in the aircraft. It should be noted that unmanned aircraft are very dependent on the avionics systems too. These comprise displays, communications, in the subtopic of today's lecture, systems which interface directly with the pilot. So as I just mentioned, all of these comprise displays, communications, data entry, control, and flight control. The display system provides a visual interface between the pilot and the aircraft system and comprises head-up displays, HUDs, helmet-mounted displays, HMDs, and head-down displays, HDD. Most combat aircraft are now equipped with HUD. A small but growing number of civil aircraft have HUD installed. The HMD is also an essential system in modern combat aircraft and helicopters. The prime advantages of the HUD and HMD are that they project the display information into the pilot's field of view, so that the pilot can head up and can concentrate on the outside world. The HUD now provides the primary display for presenting the essential flight information to the pilot, and in military aircraft has transformed weapon aiming accuracy. The HUD can also display a forward-looking infrared FLIR clear video picture one-to-one with the outside world from the fixed XLIRR or FLIR imaging sensor installed in the aircraft. The infrared picture merges naturally with the visual scene, enabling operations to be carried out at night or in conditions of poor visible due to the harsh haze or cloud. The HMD enables the pilot to be present with information while looking in any direction, as opposed to the limited forward field of view of the HUD. An essential element in the overall HMD system is the helmet tracker system to derive the direction of the pilot's sight line relative to the aircraft axis. This enables the pilot to designate a target to the aircraft's missiles. It also enables the pilot to be cued to look in the direction of a threat detected by the aircraft defensive aid system. Image intensification devices can also be integrated into the HMD. These provide a complementary night vision capability, enable the aircraft or helicopter to operate at night poor visibility. Color head-down displays have revolutionized the civil flight tech with multifunction displays, eliminated the inflexible and cluttered characteristics in 1970s generation black desks with their numerous D-dial type instruments, displays dedicated to displaying one specific quantity only. The multifunction color displays provide the primary flight displays PFD for high, airspeed, Mach number, vertical speed, artificial horizon, pitch angle, bank angle, and heading and velocity vector too. They provide the navigation display or horizontal situational indicator, HSI, horizontal situational indicator. This display, which show the aircraft position and track relative to the destination or waypoints, together with the navigation information and distance and time to go. The weather radar display can also be superimposed on the HSI display. Engine data are presented on multifunctional color displays so that the health of the engines can easily be monitored and divergences from the norm highlighted. The aircraft system, for example, electrical power supply system, hydraulic power supply system, cabin pressurization system, and fuel management systems can be shown in easy to understand line diagram format on the multifunctional display. The multifunctional displays can also be reconfigured in the event of a failure in a particular display. The communication system play a vital role. The need for reliable two-way communication between the ground bases and the aircraft or between aircraft is self-evident and is essential for air traffic control. A radio transmitter and receiver equipment was in fact the first avionics system to be installed in an aircraft and goes back as far as 1909 at the Marconi company. The communications radios used on modern aircraft is a very comprehensive one and covers several operating frequency bands. Long-range communication is provided by high-frequency HF radios operating in the band from 2 to 30 MHz. Near the medium-range communication is provided in civil aircraft by very high frequency VHF. Radios operating in the band from 30 up to 100 MHz, and in military aircraft by ultra-high frequency UHF. A radio operating in the band from 250 up to 400 MHz. You know, VHF and UHF align on side propagation systems. Equipment is usually at duplex level of redundancy. The VHF radios are generally at triplex level on a modern airliner. Satellite communication SATCOM systems are also installed in many modern aircraft, and these are able to provide very reliable worldwide communication. The data entry and control systems are essential for the crew to interact with the avionics system. Such systems range from keyboard and touch panel to use the direct voice input DVI control, exploiting speech recognition technology, and voice warning systems, exploiting speech synthesis. The flight control system explore electronic system technology in two areas, namely auto stabilization or stability augmentation systems and FBW flight control system. Most swept wing jet aircraft exhibit a lightly damped short period oscillatory motion, about the yaw and roll axis at certain height and speed conditions, known as touch roll, and require at least a yaw auto-stabilizer system to dump and suppress these modes. A roll auto-stabilizer system may also be required. The short period motion about the pitch axis can also be insufficiently down, and a pitch auto-stabilizer system is necessary. Most combat aircraft and many civil aircraft, in fact, require three-axis auto-stabilization systems to achieve acceptable control and handling characteristics across the flight envelope. Fly-by-wire FW flight control system. FBW flight control enables a lighter, higher performance aircraft to be produced compared with an equivalent conventional design by allowing the aircraft to be designed with a reduced or even navigate natural aerodynamic stability. It does this by providing continuous automatic stabilization of the aircraft by computer control of the control surfaces from appropriate motion sensor. The system can be designed to give the pilot a maneuver command control, which provides excellent control and handling characteristics across the flight envelope. Aircraft state sensor systems. These comprise the air data systems and the inertial sensor systems. The air data systems provide accurate information on air data quantities, that is the altitude, calibrated airspeed, vertical speed, and true airspeed. Certainly, it includes Mach number and airstream inside and end. This information is essential for the control and navigation of the aircraft. The air data computing system computes these quantities from the outputs of very accurate sensors, which measure the static pressure, total pressure, and the outside air temperature. The airstream incidence angle is derived from airstream incidence sensors. The inertial sensor systems provide the information on aircraft altitude and the direction in which it is heading, which is essential information for the pilot in executing a maneuver or flying in conditions of poor visibility, flying in clouds or at night. Accurate altitude and heading information are also required by a number of avionics subsystems which are essential for the aircraft's mission. For example, the autopilot and the navigation system, and weapon aiming in the case of military aircraft. The altitude and heading information is provided by the inertial sensor system. These comprise a set of gyros and accelerometers, which measure the aircraft angular and linear motion about the aircraft axis, together with a computing system which derives the aircraft altitude and heading from the gyro and accelerometer output. Modern altitude and heading reference systems, AHRS, use a strap-down or body-mounted configurations of gyros and accelerometers as opposed to the earlier gimbal. The use of very high accuracy gyros and accelerometers by measure the aircraft motion enables an inertial navigation system, INS, to be mechanized, which provides very accurate altitude and heading information together with the aircraft velocity and position data, like ground speed, track angle, and latitude or longitude coordinates. The INS, in conjunction with the air data system, also provides the aircraft velocity vector information. The inertial navigation system, or INS, is thus a very important aircraft state sensor system. It is also completely self-contained and doesn't require any access to the outside world. And now let's become to the another topic, subtopics of today's lecture. It's called navigation system. Accurate navigation information. That is the aircraft's position, ground speed, and track angle, direction of motion of the aircraft relative to the true north, is clearly essential for the aircraft mission, whether civil or military, right? Navigation system can be divided into dead reckoning, DR systems, and position fixing systems. Both types are required in the aircraft. The dead reckoning navigation system derives the vehicle's present position by estimating the distance traveled from the known position from a knowledge of the speed and direction of motion of the vehicle. They have the major advantages of being completely self-contained and independent of external systems. The main types of DR navigation systems used in aircraft are: first, inertial navigation systems, the most accurate and widely used systems. Second, Doppler hidden reference systems. These are widely used in helicopters. Third, air data or hidden reference systems. These systems are mainly used as a reversionary navigation systems, being on lower accuracy than one or two. A characteristic of all DR navigation systems is that the position error builds up with time, and it is therefore necessary to correct the DR position error and update the system from position fixes derived from a suitable position fixing system. The position fixing systems used are now mainly radio navigation systems based on satellite or ground-based transmitters. A suitable receiver in the aircraft with a supporting computer is then used to derive the aircraft's position from the signals received from the transmitter. The prime position fixing system is without doubt GPS, Global Positioning System. This is a satellite navigation system of outstanding accuracy, which has provided a revolutionary advance in navigation capability since the system started to come into full operation in 1989. There are also radio navigation aids such as VOR or DME. TACAN, which provides the range and peering R2 theta of the aircraft from ground beacon transmitters, located to provide coverage of the main air route. Approach guidance to the airfield or airport in conditions of poor visibility is provided by the ILS instrument landing system, or by later MLS microwave landing system. A full navigation suite on an aircraft is hence a very comprehensive one and can include INS, GPS, VOR or DME, ILS, MLS. Many of these systems are at duplex level, and some may be at triplex level. Outside board sensor systems. These systems, which comprise both radar and infrared sensors, systems enable all-weather and nighttime operation and transform the operational capability of the aircraft or helicopter. The radar systems installed in civil airliners and many general aviation aircraft provide weather warning. The radar looks ahead of the aircraft and is optimized to detect water droplets and provide warning of storms, cloud turbulence, and severe precipitation, so that the aircraft can alter course and avoid such conditions if possible. It should be noted that in severe turbulence, the violence of the vertical gust could subject the aircraft structure to very high loads and stresses. These radars can also generally operate in ground mapping and terrain avoidance modes. In the ground attack or mapping mode, the radar system is able to generate a map-type display from the radar returns from the ground, enabling specific terrain features to be identified for position, fixing, and target acquisition. Modern fighter aircraft generally have a ground attack role as well as the prime interception role and carry very sophisticated multi-mode radars to enable them to fulfill these dual roles. In the airborne interception, or AI mode, the radar must be able to detect aircraft up to 100 miles away and track while scanning and keeping tabs on several aircraft simultaneously, typically at least 12 aircraft. But today, like F-35, it can more than 30. The radar must also have a look-down capability and be able to track low-flying aircraft below it. In the ground attack or mapping mode, the radar system is able to generate a map-type display from the radar returns from the ground, enabling specific terrain features to be identified for the position fixing and target acquisition. The infrared sensor systems have the major advantage of being entirely passive systems. Infrared or IR sensor systems can be used to provide a video picture of the thermal image scene of the outside world using either a fixed FLIR sensor or alternatively a gimbal IR imaging sensor. The thermal image picture at night looks very like the visual picture in daytime, but highlights heat sources such as vehicle engines enable real targets to be discriminated from camouflage decoy. An IR system can also be used in a search and track mode. The passive detection and tracking of targets from their infrared emissions is of high operational value as it confers on all important elements of surprise. FLIR systems can also be installed into civil aircraft to provide enhanced vision in poor visibility conditions in conjunction with HUD. Task automation systems. These comprise the systems which reduce the crew workload and enable minimum crew operations by automating and managing as many tasks as appropriate, so that the crew role is a supervisory management function. Navigation management comprises the operation of all the radio navigation aid systems and the combination of the data from all the navigation sources, such as GPS and the INS system, to provide the best possible estimate of the aircraft position, ground speed, and track. The system then derives the steering command for the autopilot so that the aircraft automatically follows the planned navigation route, including any changes in heading as particular waypoints are reached along the route to the destination. It should be noted that this function is carried out by the Flight Management System, FMS, if installed. The autopilot and flight management system have been grouped together because of the very close degree of integration between these systems of modern civil aircraft. It should be noted, however, that the autopilot is a standalone system and not all aircraft are equipped with an FMS. The autopilot relies the pilot of the need to fly the aircraft continually with the consequent tedium and fatigue, and so enables the pilot to concentrate on other tasks associated with the mission. Apart from the basic modes, such as high hold and heading hold, a suitably designed high-integrity autopilot system can also provide a very precise control of the aircraft flight path for such applications as automatic landing in poor or even zero visibility conditions. In military applications, the autopilot system, in conjunction with a suitable guidance system, can provide automatic terrain following or terrain avoidance. This enables the aircraft to fly automatically at high speed at very low altitude, approximately near 100 to 200 feet, so that the aircraft can take advantage of terrain screening and stay below the radar horizon of enemy radar. Sophisticated FMS have come into wide-scale use on civil aircraft since early 1980 and have enabled two crew operation of the largest long-range civil jet airline. The tasks carried out by the FMS include flight planning, navigation management, engine control to maintain the planned speed or Mach number, control of the aircraft flight path to follow the optimized planned route, control of the vertical flight profile, ensuring the aircraft is at the planned 3D position at the planned time slot, often referred to as 4D navigation. This is very important for air traffic control. Certainly flight envelope monitoring and minimizing fuel consumption. The engine control and management system carry out the task of control and the efficient management and monitoring of the engine. The electronic equipment involved in a modern jet engine is very considerable. It forms an integral part of the engine and is essential for its operation. In many cases, some of the engine control electronics is physically mounted on the engine. Many modern jet engines have a full authority digital engine control system, FADEC. This automatically controls the flow of fuel to the engine combustion chambers by the fuel control unit to provide a closed-loop control of engine thrust in response to the throttle command. The control system ensures the engine limits in terms of temperatures, engine speed, and acceleration are not exceeded, and the engine responds in an optimal manner to the throttle command. The system has what is known as full authority in terms of the control it can exercise on the engine, and high integrity failure survival control system is essential. Otherwise, a failure in the control system should seriously damage the engine and hazard the safety of the aircraft. A FADEC engine control system is thus similar in many ways to a FBW flight control system. Other very important engine avionics systems include engine health monitoring systems, which measure, process, and record a very wide range of parameters associated with the performance and health of the engine. This gives early warning of engine performance deterioration, excessive wear, fatigue damage, high vibration levels, and excessive temperature levels. Housekeeping management is the term used to cover the automation of the background tasks, which are essential for the aircraft's safe and efficient operation. Such tasks include fuel management. This embraces fuel flow and fuel quantity measurement and control of fuel transfer from the appropriate fuel tank to minimize changes in the aircraft trip. Electrical power supply system management, hydraulic power supply system management, cabin or cockpit pressurization systems, environmental control systems, warning systems, maintenance and monitoring systems. These comprise monitoring and recording systems, which are integrated into an onboard maintenance computer system. This provides the information to enable speedy diagnosis and rectification of equipment and system failures by pinpointing faulty units and providing all the information such as part number for replacement units down to module level in some cases. The above brief summaries cover the roles and importance of the avionics system shown in this slide. It should be pointed out, however, that there are several major systems, particularly on military aircraft, which have not been mentioned. Space constraints limit the coverage of the system shown in this failure to display, data entry and control, flight control, inertial sensor systems, navigation systems, air data systems, autopilot, and flight management systems. Yes, certainly data buses and avionics systems integration. It is not possible to cover communications, radar, infrared systems, engine control, and housekeeping management. The visible impact of the avionics system on a modern aircraft can best be seen in the cockpit, where the outputs of the various systems just described are displayed on the HUD, HMD, and the color AGD. And this figure shows the fifth generation fighter aircraft, which is in service with the Air Force of the USA, UK, Germany, Italy, and Spain. The aircraft is a high agility single-seat fighter for strike aircraft with an outstanding performance. The foreplane and ailerons provide positive trim lift, as it is highly unstable in the pitch at subsonic speed. Time to double pitch amplitude following a disturbance is around 4.1 seconds. It is also enabled in yaw at supersonic speed because of the reduced fin size. The high integrity FDW flight control systems compensate for the lack of natural stability and provides excellent control and handling across the flight envelope and under all loading conditions. The F-35 pilot is equipped with a sophisticated binocular HMD and sighting system, which is shown in this slide. Miniature night vision cameras are mounted on each side of the helmet, and the binocular video image are displayed on the HMD. The infrared video image seen from the gimbal infrared sensor can also be displayed on the HMD to provide a complementary night vision system. And this slide shows the Airbus A380 long-range airline, which entered airline service in 2008. The A380 is the largest airliner in the world and can carry up to 800 passengers. The advanced flight test of the A380 can be seen in this slide and features 8 multifunctional high-resolution color LCD flat panel display. and optimized layout of the multifunctional displays ensures that each of the two crew members can easily assimilate all relevant data. The screen being sized so that no eye scanning is necessary. In front of each pilot is a primarily flight display and a navigation display. The remaining two screens display engine and system data. The pilot side stick controllers can be seen at the sides of the flight deck. The FBW flight control systems eliminate the bulky control column between the pilot and instruments of earlier generation aircraft. This ensures an unobstructed view of the display. There are also three multi-purpose control and display units, which, in addition to accessing the flight management system, are also used to give systems maintenance data in the air and on the ground, certainly. The two large screen displays at the sides of the A380 flight deck are able to display, for example, comprehensive airport data, including the airport layout, runways, etc. They can also be used to display relevant information from the flight manual, emergency procedures, and the central multifunctional displays on the flight deck can also be reconfigured to display video images from monitoring cameras installed in the aircraft. The flight deck of the other members of the Airbus range of airliners, the A320 and its derivatives, the A318, A319, and A321, the A330, and the A340 are basically very similar to that of the A38, but lack the large screen display at each side of the A380 flight deck. And now we begin to the next part of our lecture. It calls the avionic environment. Avionic systems equipment is very different in many ways from ground-based equipment carrying out similar functions. The reasons for these differences are briefly explained in view of their fundamental importance. The importance of achieving minimum weight, the adverse operating environment, particularly in military aircraft, in terms of operating temperature range, acceleration, shock, vibration, humidity range, and electromagnetic interference. The importance of very high reliability, safety, and integrity. Space constraints, particularly in military aircraft, requiring and emphasizes on miniaturization and high packeting density. The effects on the design of avionic equipment to meet these requirements can result in the equipment costing up to 10 times as much as equivalent ground-based electronic equipment. There is a great effect on unnecessary weight, which is of the order of 10 to 1. For example, a weight saving of 10 kilos enables an increase in the payload capability of the order of 100 kilos. The process of the effect of additional weight is a vicious circle. An increase in the aircraft weight due to, say, an increase in the weight of the avionic equipment requires the aircraft structure to be increased in strength and therefore made heavier in order to withstand the increased loads during maneuver. Assuming the same maximum normal acceleration achieved, okay, and the same safety margins on maximum stress level are maintained. This increase in aircraft weight means that more lift is required from the beam, and to be accompanying drag is thus increased. right? An increase in engine thrust is therefore required to counter the increase in drag, and the fuel consumption is thus increased. Are you agree with me? Nice. For the same range, it is thus necessary to carry more fuel, and the payload has to be correspondingly reduced. Or if the payload is kept the same, the range is reduced. For this reason, tremendous efforts are made to reduce the equipment weight to a minimum, and weight penalties and can be imposed if equipment exceeds the specified weight. The environment in which avionic equipment has to operate can be a very severe and adverse one in military aircraft. The civil aircraft environment is generally much more benign, but it is still an exacting one. Considering just the military cockpit environment alone, such as that experienced by the HUD and HDD. The operating temperature range is usually specified from -40 centigrade and up to 70 centigrade. Really, the pilot will not survive at this extreme, but if the aircraft is left out in the Arctic cold or soaking in the Middle East sun, for example, the equipment may well reach such temperature. I hope you agree with me, right? A typical specification can demand full performance at 2,000 feet within 2 minutes of takeoff at any temperature within the range. Vibration is usually quite severe, and in particular, airframe manufacturers tend to locate the gun right under the display. Power spectral energy levels of 0.04 G squared per hertz are encountered in aircraft designed in 1970s, and levels of 0.7 G squared per hertz at very low frequencies are anticipated in future installations. It is worth noting that driving over cobblestone will give about 0.001 G squared per hertz. The equipment must also operate under the maximum acceleration for G to which the aircraft is subjected during maneuvers. This can be 9G in a modern fighter aircraft, and the specification for the equipment would call up at least 20G. The electromagnetic compatibility EMC requirements are also very demanding. The equipment must not exceed the specified emissions level for a very wide range of radio frequencies, and must not be susceptible to external sources of very high levels of RF energy over a very wide frequency band. This equipment must also be able to withstand lightning strikes and the very high electromagnetic pulses, EMP, which can be encountered during such strikes. Design of electronic equipment to meet the EMC requirements is in fact a very exacting discipline and requires very careful attention to detailed design. The overriding importance of avionic equipment reliability can be appreciated in view of the essential role of this equipment in the operation of the aircraft. It is clearly not possible to repair equipment in flight, so that equipment failure can mean aborting the mission or a significant loss of performance or effectiveness in carrying out the mission. The cost of equipment failure in airline operations can be very high. Interrupted schedule, loss of income during aircraft on the ground situations, etc. In military operations, aircraft availability is lowered and operational capability lost. Every possible care is taken in the design of avionic equipment to achieve maximum reliability. the quality assurance (QA) aspects are very stringent during the manufacturing processes and very frequently call for what is referred to as reliability shakedown testing, or RST, before the equipment is accepted for delivery. RST is intended to duplicate the most severe environmental conditions to which the equipment would be subject, in order to try to eliminate the early failure phase of the equipment life cycle. All failures in service and in testing certainly are investigated by the QA team and remedial action taken if necessary. The overall cost differential in meeting all the factors imposed by the avionic equipment environment can thus be appreciated. The SI unit of mass is a kilogram. I hope you remember that. And the unit of length is a meter, right? And the unit of time, yeah, the second, certainly. The SI unit of temperature is the Kelvin. 0 degrees Kelvin corresponding to the absolutely lowest temperature possible, at which almost all molecular translation motion theoretically stops. To convert temperature in degrees Celsius to the degrees Kelvin, it is necessary to add 273 and 15 centigrade. And thus, 0 Kelvin equals minus 273.15 Celsius. The SI unit of force is a Newton. I hope you remember. 1 Newton being the force required to accelerate a mass of 1 kilogram by 1 meter per second. Converting to pound, foot, second unit, the Newton is approximately equal to a force of 4.22 pound weight. The apocryphal story of an apple falling from Newton's hat, triggering of the theory of gravitation, gives an appropriate twist to the unit of the Newton. As an average apple weighs about 4.22 pounds, and figures in this slide illustrate the pressure in the SI system is measured in Newton per square meter or Pascal. The millibar, which is equal to 10 in power minus 3 bar, is also widely used, the bar being derived from the barometry. 1 bar corresponds to the atmospheric pressure under standard sea level conditions and is equal to 10 in power 5, not 105. It should be 10 in power 5 newtons per square meter. Or 100 kilopascals, and 1 millibar is equal to 100 Newton per square meter or 100 pascals. Altitude is quoted in feet, as this is the unit used to the air traffic control authorities, and altimeters in the USA and the UK are calibrated in feet. Speed is also quoted in kiloknot, as this unit is widely used in navigation. 1 kiloknot is 1 nautical mile, nm, per hour, 1 nautical mile. And 1 nautical mile is equal to the length of the arc of the Earth's surface, subtended by an angle of 1 minute of arc, measured from the Earth's center, and can be related directly to latitude and longitude. 1 nautical mile equals 6,076.1155 feet, or 1,852 meters exactly. The conversion from kiloknots to meter seconds is given by 1 kiloknot equals 0.5144 meters per second. And conversely, 1 meter per second gets us 1.94 kiloknot. a useful approximate conversion is 1 kiloknot. A kiloknot is approximately half meter per second. Yes, or 1 meter per second get us approximately 2 kiloknots. I think this is enough for beginning, right? And now I want to propose you some useful books you may read during study hour 4. I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.